This is a comprehensive short documentary that will discuss the formation of Tasmania, the link between it and the Grand Canyon, and the collision between East and West Tasmania. Hope you find this video to be informative.
Tasmanians are different from their mainland counterparts. Well, at least they are in a geological sense, and many others too. Jokes, love you guys. But truth be told, Tasmania wasn't originally part of Australia at all. I know, right? Insane. But it's actually far older than the entire eastern portion of Australia. And the actual rocks that make up the basement foundation of Tasmania were derived from some very foreign places that are located in vastly different spots around the world today. In this video, we're going to take a look at the formation and eventual joining of Tasmania to Australia. Tasmania is old. Very old. It has Mesoproterozoic rocks that were deposited at some point between 1.6 to 1 billion years ago. Not only is Tasmania old, but the composition and construction of its earliest form is actually owed to the ancient assemblage of different continental pieces of crust. Meaning Tasmania was originally made up and comprised of sediment weathered from two completely separate continents. But to go back to the start, Tasmania was originally part of the supercontinent known as Nuna. Nuna existed around 1,750 million years ago, and the rocks that make up Proto-Tasmania are actually related to rocks that existed and still exist in East Antarctica and North America, primarily within the state of Arizona. Because of this, some scientists consider Tasmania as a microcontinent in its own right. But how did it all actually start? Well, much like the origin of Eastern Australia, Tasmania was also constructed from an area that was once a deep sea. For many tens to hundreds of millions of years, this deep sea would be filled by sediment, carried into it by the rivers from Antarctica and North America. This sediment would accumulate on the continental shelf, right at the edge of the border between the ocean and the deep ocean. And eventually, the accumulation of this sediment would result in massive underwater landslides. Turbidity currents can carry the sediment for very vast distances when these landslides occur. So at this point, you might start to form an idea of what Tasmania's early life was like. It was sandwiched between two major continents, and the eroded sediment from them was slowly laying down the foundations required for the landmass known as Tasmania to be constructed. Back then, Australia and Antarctica were located in the Northern Hemisphere, but this is going back quite far in time, so the accuracy of depicting or even totally deciphering how Nuna looked is limited. Tasmania really began its independent life around 1,400 million years ago, when a tectonic rifting event occurred, forcing the separation of North America from Antarctica. As this tearing apart of the landmasses occurred, the sea slowly made its way inland, and part of Tasmania was torn away from it and left attached to North America, whilst another part of it was left attached to Antarctica, where these pieces still exist today. This collision helped to uplift Melbourne out of the deep sea, and Victoria as we know it has this collision to thank for part of its construction and modern day appearance, as this collision sparked another mountain building event in Victoria. And, well, as I've said before, where mountains are built, minerals are injected, and Victoria's mineral enrichment definitely has this, alongside many other orogenies, to thank for its major mineralisation. But it's not just Victoria. Tasmania also got very mineral enriched from this tectonic collision, as this event created the Mount Reid volcanic belt. So in the millions of years that followed, Tasmania would ride alongside Australia. There would be periods of tectonic stretching, followed by compression, followed by nothing for millions of years. Highlands would form, erode, and be replaced by more mountain building events, and life would slowly evolve to take over the land. Eventually, Gondwana would break apart, and Tasmania lost its friend to the west when Antarctica slowly drifted away from it, with it completely breaking free about 45 million years ago. Prior to the recent rise in ocean water levels, Tasmania was actually accessible via a land bridge from Victoria, and Australian Aboriginals took that path and inhabited the lush, wet, resource-rich lands of Tasmania. Then, as the sea levels rose, it was isolated again, and water inundated and drowned out this land bridge, cutting off Tasmania and leaving it as a landmass in its own right, yet again. So this is the story of the construction of Tasmania. It truly is a different place. But regardless of that, it's still as Aussie as any part of this great country. Thanks for watching.
When you think about Tasmania, you probably think about a verdant wilderness, untouched beauty, the Tasmanian devil, and maybe the Tasmanian tiger. What you don't think of is the Grand Canyon, true? Well, it might surprise you to hear that Tasmania shares a very close link to the United States, and a particularly intriguing relationship has been found between it and the Grand Canyon. The fact is, Tasmania is old, really old. It's a little over 1 billion years older than Victoria, New South Wales, and much of Queensland. The connection between it and the United States takes us back over 1 billion years, revealing a story about the supercontinent Rodinia. I originally made a video that delved into Tasmania's rich geological origin a little over a year ago. In this video, we're going to take a closer look at the evidence that exists which links these two landmasses in detail. Tasmania is an ancient microcontinent. It only collided with Australia some 500 million years ago. In its early construction, Tasmania was constructed from sediments that flowed from the rivers of North America and Antarctica into a deep ocean. These ancient sediments are what Tasmania in present day is composed of. A rift event then occurred which tore Tasmania away from the North American landmass, leaving sections of it in North America, whilst the rest of it drifted away as a lone microcontinent. It originally existed in the Northern Hemisphere, but it has ended up an ocean away from the American landmass. To understand the link between Tasmania and the Grand Canyon, we must first delve into the concept of supercontinents. Rodinia was an ancient supercontinent that formed about 1.1 to 1 billion years ago. Unlike the more famous Pangaea, Rodinia existed in a much earlier geologic era known as the Proterozoic Eon. During Rodinia's existence, what is now Tasmania and parts of North America were neighbours. Geological evidence suggests that Tasmania was positioned along the margin of Laurentia, a large landmass that forms the craton or ancient core of present-day southwestern North America. The key to unravelling this ancient connection lies in the study of rocks and sediments from that era. In recent years, geologists have discovered that certain rock formations in Tasmania share remarkable similarities with those found in the Grand Canyon's Unkar group. These rock formations are not only similar in age, but also in their geochemical compositions. The Unkar group in the Grand Canyon contains sedimentary rocks that were deposited during a significant geological event known as the Grenville orogeny. This mountain building period occurred between 1.3 and 1 billion years ago, and left behind a series of basins filled with sediments. These basins, known as foreland basins, were formed as the land was compressed and deformed by the tectonic forces of the mountain building event. A foreland basin is essentially a structural depression that forms adjacent to a mountain range, due to the immense weight of the mountains and the tectonic forces involved in their creation. This basin stretched across what is now the southwestern United States, encompassing areas such as present-day Texas, New Mexico, Arizona, and into parts of California. In this foreland basin, thick sequences of sedimentary rocks were deposited. The sediments came from the erosion of the rising Grenville Mountains, which transported vast amounts of material into the basin. Over time, these sediments were compressed and lithified into the rock layers we see today. In the Grand Canyon, these layers are known as the Unkar group, which includes dolomites, shales, and quartz arenites that are around 1.25 to 1.15 billion years old. Similarly, in Tasmania, the Rocky Cape group represents a comparable sequence of rocks. The sedimentary layers in the Rocky Cape group mirror those of the Unkar group, both in age and composition. This suggests that during the Mesoproterozoic era, Tasmania was located along the same tectonic margin as southwestern North America and experienced similar geological processes. The tectonic setting that led to the formation of this foreland basin was complex and involved the convergence and collision of continental plates. As these plates pushed together, they not only created mountain ranges, but also generated the conditions necessary for the formation of extensive sedimentary basins, like the one that houses the Unkar and Rocky Cape groups. As Rodinia began to break apart, these basins were left as remnants of the ancient geological processes. The discovery of similar rock sequences in Tasmania and the Grand Canyon has provided geologists with crucial insights into the paleogeographic reconstructions of Rodinia and the ancient positions of its constituent landmasses. So in Tasmania, the Rocky Cape group represents a similar sedimentary sequence, with rock layers that mirror those found in the Unkar group. Both regions contain an older package of dolomite and shale dating back to around 1.25 billion years ago, topped by quartz-rich sandstone from about 1.15 billion years ago. This stratigraphic similarity provides compelling evidence that Tasmania was once part of the same geological environment as the southwest Laurentian region. But it wasn't only the Tasmanian landmass that has these similarities. Before the recent rise in sea level, Tasmania was connected to mainland Australia, and the island known as King Island was a mountainous peak. But King Island also contains the same Rocky Cape geological group as Tasmania does, showing it was once also connected to North America too. As you can see, the entire island is comprised of this geological group, which isn't surprising as the microcontinent of Tasmania actually stretches into far north Victoria, so it's much larger than the island we know and love. Further evidence comes from the study of zircon minerals, which are used in uranium-lead dating to determine the age of rocks. This method is one of the oldest and most reliable dating techniques, often used to date ancient rocks and geological events. These minerals also carry isotopic signatures that reveal information about the rock's origins. In both the Unkar and Rocky Cape groups, zircon analysis indicate derivation from a crust dating back 1.8 to 1.4 billion years ago, similar to the basement terrains in southwest Laurentia. The presence of these similar rock formations on opposite sides of the world suggests a fascinating geological history. During the time of Rodinia, Tasmania was likely connected to southwest Laurentia, and the sediments that would become the Rocky Cape and Unkar groups were deposited in a continuous basin along the margin of this supercontinent. As Rodinia began to break apart around 750 to 633 million years ago, these landmasses drifted to their current positions. The separation was driven by the forces of plate tectonics, which continue to reshape the Earth's surface to this day. It's quite hard to get an accurate picture of ancient supercontinents, and things only get murkier as you travel further and further back in time. But through the careful analysis of rock formations, we are slowly piecing together the history of the Earth, one fragment at a time. I hope you found this video to be as interesting as I did, and as always, thanks for watching. Tasmania is an ancient land. At least most of it is. The western part of it is up to 1.6 billion years old, but the east, well, that's a completely different story. It might surprise you to learn that the two parts of the island collided together at some point during the early Devonian period, roughly 400 million years ago. We're going to do a deep dive into the details of the collision in this video. Tasmania drifted for around 150 million years as a lone microcontinent known as Van Dieland, before inevitably colliding with Western Victoria, where it sutured to the landmass around the Bacchus Marsh area, beginning around 500 million years ago. At this point in time, Tasmania looked like this. King Island existed, and Western Tasmania did too. Flinders Island and the eastern section of Tasmania, however, wouldn't exist as a subaerial landmass until the Devonian period, when the Lachlan origin took place. The Lachlan origin refers to a series of geological events that shaped much of eastern Australia, including eastern Tasmania. These events occurred over a prolonged period during the Paleozoic era, primarily spanning from the Ordovician to the Devonian periods, approximately 480 to 360 million years ago. Before we go further, it's worth visiting the videos that I released on Flinders Island. In it, I documented how the island came into existence. Eastern Tasmania is closely related to the processes that uplifted Flinders Island, and the video is definitely worth watching to get a greater understanding of the processes that occurred. Eastern Tasmania and Flinders Island share the same batholithic granite intrusions. These now solidified enormous ancient magma chambers were emplaced into the crust at the same time. Flinders Island is known for a gemstone known as the Killiecrankie diamond. Contrary to the name, the gemstone is actually a brilliant topaz that looks very similar to a diamond. It's so similar in appearance that early gemologists in the 1800s had trouble understanding the difference between the two, and it was only with advancements in technology that we were able to work out that it was a topaz and not a diamond. The reason I'm mentioning this gemstone is because it likely exists beyond the shores of Flinders Island. The very same granite that shed this gemstone on Flinders Island exists in eastern Tasmania, and thus the Killiecrankie diamond likely exists on the mainland much like it occurs on Flinders Island. So let's take a look into where the collision occurred in Tasmania and what forces drove it. To understand this, we need to look into the Tamar Fault Zone. It's a major fault system in Tasmania that separated two continental plates. It's also known as the Tamar Fracture System. The Tamar Fault Zone is the boundary between these two continental plates, similar to the San Andreas Fault System in North America. The Tamar Fault Zone also corresponds to the Victorian Governor Fault. This is the same fault that I outlined in my video on Flinders Island, showing the connection between Tasmania, Flinders Island, and Victoria. It's worth remembering that at this point in time, Australia was joined to Antarctica and was known as Gondwana, a supercontinent that includes Australia, Antarctica, India, Africa, and the Americas to name a few. And Australia and Antarctica wouldn't fully break apart until 80 million years ago, with the rift event beginning some 160 million years ago. So we have West Tasmania, Australia, and Antarctica sandwiched together 400 million years ago. Now I mentioned that the collision that occurred was a continent-to-continent one. This means East Tasmania was likely a lone microcontinent or a series of smaller terrains before it sutured with Western Tasmania. Eastern Tasmania's origin is tied to subduction and accretion processes along the Gondwanan margin. It likely formed as a fragment of the Lachlan origin, which included volcanic arcs, back arc basins, and accreted sediments. So the subduction events that occurred during the events that made up the Lachlan origin are likely responsible for birthing the eastern portion of Tasmania. This suture zone reflects the closure of the intervening ocean or back arc basin, consistent with microcontinent or terrain collision dynamics. The east was geologically distinct from Western Tasmania until their collision during the Tabarabran orogeny in the Devonian. I mentioned the Tabarabran orogeny in depth as it relates to Flinders Island in the video I made on that, and here's what I said. The Tabarabran orogeny, occurring during the Middle Devonian around 385 to 380 million years ago, was a brief yet intense tectonic event that reshaped southeastern Australia, affecting regions in Victoria, New South Wales, and Tasmania. Driven by tectonic compression along the eastern edge of Gondwana, this orogeny caused widespread folding, faulting, uplift, and crustal thickening. The compression generated enough heat to partially melt the crust, resulting in significant granite intrusions that are visible today due to later uplift and erosion. This event marked a major transition, ending marine sedimentation and uplifting previously submerged regions above sea level, subjecting them to erosion and forming rugged landscapes. And it's likely that along with being uplifted from the deep sea, Flinders Island's first glimpse at subaerial life involved the development of a mountain range, or at the very least an elevated terrain that has completely eroded today, unveiling the once deep granitic batholiths, which were previously vast deep magma chambers that never made it to the surface to erupt, and instead cooled and solidified, only to be later uplifted. This orogeny was a major mountain building event that occurred during the Devonian period around 390 to 380 million years ago. This process involved oceanic crust being consumed beneath the continental crust, which built volcanic arcs, accretionary wedges, and other features typical of subduction zones. Over time, as the oceanic basin between East Tasmania, or the associated terrains, and the West Tasmanian landmass narrowed, continental collision occurred during the later stages of the orogeny. This was when the terrains and microcontinental fragments were sutured to the Gondwanan margin, marking the final stages of the orogenic event. Subduction zones and tectonic compression played a central role, closing ocean basins and deforming the crust. So how do we know the East and West are separate entities? Well, there's a few reasons. One of the major indicators are the contrasting geology that exists between the East and West. West Tasmania is dominated by ancient Precambrian rocks that are 1.6 billion years old at their oldest, while East Tasmania consists of Paleozoic sedimentary and volcanic rocks associated with the Lachlan origin that are dated to being deposited within the past 538.8 million years. Another indicator is the deformation and metamorphism patterns that are consistent with continental collision and crustal thickening. And lastly, the Tamar Fracture Zone is a clear geological boundary running through central Tasmania that very noticeably marks the suture between the older West Tasmanian block and the younger East Tasmanian terrains. The collision caused crustal thickening, regional metamorphism, and the intrusion of granitic magmas into the crust. As you can see, there are many granitic intrusions that exist in the east, and the emplacement of them all occurred around the same time, including the granite that exists on Flinders Island. So, whilst East Tasmania and Flinders Island are separated by a body of water, it was only recently that the inundation of this area occurred. The Tamar Valley occupies the Tamar Graben, a geological structure defined by a series of parallel northwest trending faults. A graben forms when the Earth's crust is subjected to extensional forces. The Tamar Fracture Zone was affected by the rifting event, and for a good reason. After all, it's plausible that the Tamar Graben and the associated stretching forces align with the suture zone between East and West Tasmania, which is a major weak point in the crust. The resulting narrow trough, some 50 kilometers long and 5 kilometers wide, has been partially infilled with soft sands, clays and gravels, with intercalated basalt flows in places, of mainly a Paleogene, lower tertiary age of 66 million years ago to 23 million years ago. Low hills of hard Jurassic dolerite deposited between 201.3 to 145 million years ago define a structure on either side. The graben was formed during the breakup of Gondwana, during the separation of Australia from Antarctica in the Cretaceous early Cenozoic period, some 70 to 140 million years ago. However, the breakup forces were not specifically trying to pull East and West Tasmania apart. Instead, the forces acted on Tasmania as a whole, exploiting pre-existing structural weaknesses like the Tamar Fracture Zone. With that being said, it's very possible that the two could have been pulled apart if the force was great enough, but thankfully it wasn't, and it is known as a failed rift. Instead, the crust cracked and sagged as it was torn apart, opening up the land to form a valley, that we call the Tamar Valley today. So this is the story of the collision between East and West Tasmania. It occurred around 400 million years ago. It was driven by the subduction events that make up the Lachlan origin. The eastern part of Tasmania was likely a lone microcontinent or a series of terrains that were created during the earliest subduction events that the Lachlan origin is comprised of. Volcanic arcs, back arc basins and accretionary wedges formed along the margin of the ancient supercontinent Gondwana, contributing to the development of these terrains. Over time, these smaller landmasses were pushed towards western Tasmania due to tectonic forces. This culminated in a continental collision around 390 million years ago during the Devonian period as part of the Tabarabran orogeny. During this collision, the Tamar Fracture Zone formed, marking the suture where East and West Tasmania were welded together. The collision caused significant deformation, including folding, faulting and metamorphism of the rocks in the region. Granitic intrusions associated with this event further solidified the union between the two regions. Thus, East and West Tasmania became a single landmass, though their contrasting geological histories remain evident. The West is dominated by ancient Precambrian rocks, while the East showcases younger Paleozoic formations, highlighting their different origins and the dramatic tectonic forces that brought them together. I hope you found this to be as interesting as I did, and as always, thanks for watching. Before I end this video, I'd like to give a big shout out to my Patreon and YouTube members. Thank you so much to everyone that helps to support this channel.